All right, there we go. Let's get my screen shared here. And all right. Good morning, good afternoon, everyone. Thank you for spending your time with us today to discuss some SQL Server encryption basics. My name is Bob Pusateri, and just as a brief introduction here, I run a blog at bobpusateri.com. I'm a friend of Redgate. You can reach out to me on Twitter at SQLBob. I'll have all that information at the end as well. I'm a Microsoft Certified Master, and I'm one of the co-chapter leaders of the Chicago SQL Server User Group, which is a past chapter. So a brief summary of today's session. This is an introductory 100 level session, and basically we're going to introduce some general encryption terms and then SQL Server's usage of those terms and other SQL Server specific encryption terms, and talk about and introduce SQL Server's encryption capabilities. So to start off with, why are we bothering with encryption? Typically, we as DBAs are bothering with encryption because someone told us to. Someone says it's necessary. And that someone could be a bunch of different people depending on your organization. Maybe baked into existing company policy, maybe a requirement of your company's insurer. They will not offer insurance if you do not offer encryption for your data. Or maybe it's your own legal department that says encryption. There we go. Now I'm unmuted. Okay, I don't know what happened there. Pardon me. Maybe it's a legal requirement, or perhaps it's a government requirement, and there are actual laws that says this data must be encrypted. Whatever the reason is we're encrypting, when it boils down to is we have some sort of secret in the database that's important, and we don't want them getting out. And these secrets can take many forms. The most common would, of course, be the data itself. Maybe you have sensitive personal information about people, medical data, healthcare data, something along those lines. But there's also other secrets in the database that need protecting, whether or not your data itself is sensitive. So maybe there's linked server passwords that can access other machines in your environment. Operating system passwords, right? SQL Server executes as a service account. It needs a password. That password needs to be stored somewhere. So that's in there as well. There's also encryption keys, so information that protects other information, and these are secrets as well. Those need protecting. And what are we protecting this from? Who does the organization trust, for example? So there's many people in an organization. Do we trust maybe the end users with this data? Maybe not, depending on their role. They're the IT employees or the DBAs. How about the executives? How about the owner of the company? And as a short story from that, I use personal budgeting software. I'm a big believer in personal budgeting. As a product called You Need a Budget that I use, and they were previously a local installed product, but recently in the past year they've gone to a web offering. And they had a massive downtime a couple months ago, lasted better part of a day with their online web product, which was really not good for them because they had just launched it. And afterwards, after they got it back up, they announced what happened. And it turned out that the owner of the company himself was deciding to make some changes with DNS settings, and he was very, very sorry he did that as it took the entire product down. And he actually posted on the blog that he no longer has DNS access. That's not something he, as the owner, really needs to worry about. He has an IT staff for that. So, who do you trust? Whether or not they have good intentions, bad things still might happen. So our goals with encryption, why we're doing this, number one, prevent theft of data. We don't want our data getting out, our secrets. If it does get out, we want to make it not worth the effort to try using it. And if it's encrypted well, then generally that won't be possible. Sometimes the mere fact that we have encryption will make our system less of a target.
Hey Bob, we seem to have lost your sound. Are you still talking?
That's weird. It just said it muted itself. I'm sorry. Okay, how long ago did you lose my sound?
On the right at the very end of the last page, just as you
Okay,
right before you showed comply with underscore.
interesting. Okay, my apologies. Um, so yeah, we're looking to make our system a more difficult target than any other system, simply because we have encryption. And finally, we're looking to comply with something. We don't, it might be a law, might be an internal policy, might be, as we said, we were different reasons why encryption might be required. So SQL Server has three different basic types of encryption. As mentioned, the first is hashing. So hashing is a one-way method of encryption. So you have a value. You create a hash of that value. A hash is typically a long, complicated string consisting of letters and numbers. We'll demonstrate that shortly. Hashing is great for comparisons. Usually you would use this to protect something like a password. In fact, SQL servers own SQL login passwords. So if you create a login and have it be a SQL Server login where it's a username with a password that you can assign and change within SQL Server, those are actually stored as hashes. Moving up to a little more complicated method, we have symmetric key encryption. So this is the most common type of encryption you'll find in SQL Server. Symmetric key encryption is very fast, and it's used to protect most of the data you'll find in SQL Server. Service master keys, database master keys. And because it's symmetric key encryption, the same key is used both to encrypt and decrypt the data. This presents an interesting problem because now if you need to send that encrypted data somewhere, you also need to make sure the key is there to decrypt it as well. And there's a variety of different methods that can be used to share that key securely between different parties, since it will be necessary on both sides. And then finally, we have asymmetric key encryption, and this is slower, but the key comes in two parts now. You have what is a public key, which is part of the key that you broadcast to the entire world, and you have the private key, which you keep to yourself and never share with anyone. The advantage of asymmetric key encryption is you don't need to share the entire key. You only need to share part of it. So that we're looking takes away the problem of needing to transport the entire key securely. So to dive a little deeper into this with hashing, as I said, hashing is taking a value and transforming it into a different value, a sequence of bytes, and this value is known as a hash. So if we were to hash the string SQL using a SHA-2 256-bit hash, that would be the result there, that nice long string there. Hashing is guaranteed to produce the same value, or the same hash value, for the same starting value. So I could hash SQL using a SHA-2 256-bit hash. From now until the end of time, I should always receive the same value I put on the screen here. Different values that are hashed are extremely likely to produce different hashes. This is the idea. Occasionally you will find different values that can produce the same hash. This is known as a collision. These are supposed to be extremely rare, and as your hash algorithm gets stronger, the chances of a collision continues to decrease further and further. And finally, with hashing, if you only know the hash value, it's going to be very difficult to find the value that was used to create that hash value, unless you've already created a hash from it. So if I were to hand you that long hash of SQL above and say, what value was this, you'd really have no way of knowing that was a hash of SQL unless you had calculated that ahead of time. And if you calculate that ahead of time, that is typically known as a rainbow table. They can be used for different types of attacks, but basically it involves hashing all kinds of strings and storing them so that you can look up by the hash value. I should point out that a hash is not a checksum. Checksums are designed for error checking data very quickly, but not necessarily for security. Checksum algorithms have improved over time as well, but they are essentially an extremely simple type of hash. One of the very old checksum methods, CRC, the cyclic redundancy check, that only produces 256 values. So if you were to use a CRC, your chances of having a collision are only 1 in 256, which is extremely likely as far as hashing goes. Later they came out with CRC32, which produces 2 to the 32nd values, which is, chances are 1 in approximately 2.7 billion, or whatever the value of an integer is. But most of the modern hash algorithms are significantly stronger than this. These algorithms were used back in the day when CPUs were slower and didn't have the power. They certainly do. Now, a SHA-1 or an MD5 are much more common, and the SHA-2 family of hashes is even better. SQL Server has lots of hashing algorithms available depending on your version. If you needed to hash something in SQL Server, as we'll see in a demo here very shortly, there's a function called hash bytes, returns a var binary value. You have a choice of many different algorithms to use. The longer your number of bytes in your hash algorithm are, the harder your hash is to crack, and the less likely they will be to create a collision or have a duplicate. The two algorithms that are bold here, the SHA-2 256 and 512, are the only algorithms that are not deprecated in SQL Server 2016. All the others, MD2, MD4, 5, SHA, and SHA-1, still available, but they're now deprecated in 2016. So if you're doing any new development that involves hashing at this point, you would most definitely want to use a SHA-2 256 or 512. So we're going to go here and do a quick demo on hashing. This is actually our only demo in this session. So we have our SQL script here. We're going to start by creating a database just called hash demo and using it. Just to demonstrate how hashing works, we're going to use the hash byte function with the SHA-2 256, and we're going to hash the word SQL Saturday. So as we can see here, and I know this is kind of small, so I'll zoom in. This is the value that is the hash produced by the value SQL Saturday. Now, just to show how hashes work, if we were to change just one character in the value we're hashing, so instead of SQL Saturday, we're going to change that final Y to an X. We're going to hash SQL Saturdax instead of SQL Saturday. We'll do the two of these together here now, and you'll see that even though only the final character differs, the entire hash result is different. Even though only the last character, it's not like just the last character is different, so the last few characters of the hash will differ. The entire hash is completely different with simply one character changing. To show a stronger hash algorithm, we're going to use the SHA-2 512 now and just show that produces a result that is twice as long as the 256. So here's our 256 values we just demonstrated. Now if we were to expand the 512s, you'll see that a 512 is significantly longer, in fact, twice as long. You can only imagine how much less likely you are to produce a collision using the 512 algorithm as opposed to the 256. As I mentioned, one of the most common uses of hashing is for storing usernames and passwords. So we have a little part of this demo is this as well. Let's pretend we have an application here and we're trying to store user login information. So every user has an ID and a username. In this table, for demonstration purposes only, we're going to store the password in plain text, which you should never do in reality, but we're doing it here for demonstration purposes only. And you should store the hash of the password. So we're creating our table with these 4 columns. We're going to create a procedure that will add a user to this table, and it will basically fill in the username, the password, and the password hash into the table. So we're going to create a user. We're going to create a user with a username of Adam, and Adam's password is swordfish. And if we now select from the user info table, you'll see here we have our user, his plain text password, and then the hash of that plain text password. So that's what we're doing here. We're going to add a few more users now. We got Bob, Cindy, and Donnie we're throwing in. And you'll notice that Bob and Donnie both have the same password. They both decided to choose the word elbow as their password. So if we now select from this user table again, you'll see we have 4 users in there now, and Bob and Donnie's passwords are identical, and thus the hashes for their passwords are also identical. This can pose a problem simply because if I'm Bob and I'm looking at this table, if I had access to it, I don't know what Donnie's password is, but if I can see that Donnie's hash is the same as mine, well, then his password is the same as mine too, and I can go log in and pretend I'm Donnie now if that's what I wanted to do. So a way to get around this is a procedure known as salting, which is you take an extra value and add that in with your hash. So in this case, it's a very simple salt. I've created this procedure, and it is setting the password hash now. Instead of just hashing the password, it's also going to throw the user ID in there as well. That's going to make each value different. So we'll create this procedure here, truncate our user table, and re-add these 4 users with the same passwords again. And now if we look at our results, you'll see we still have the same users with the same passwords, and Bob and Donnie still both have elbow as their password, but now their hashes are completely different due to the salt being present in that hash. So even if I had access to this table and it didn't contain the plain text passwords, I would have no way of knowing anyone else had an identical password to me because the hashes are no longer identical. They're different because of the salt. And then finally, if you wanted to fill out this application a little more and add a procedure to check the password, perhaps to verify that the user passwords are correct, we can do that as well. And that's rather simple. All we're doing is returning a value, a 1 or a 0. You never want to tell people whether or not, your username is not a valid username. Oh, I guess I just have to guess a new username then. You just want to say, does this pair of username and password match or not? So if we create this function here and check the password, let's pretend we're checking a password for a user named Eileen, which Eileen doesn't exist. We never put one in there. So you'll notice this just simply returns a 0. And user doesn't exist. It's just for our own reference, so we know what's up with that. I wouldn't return that to a user. If we check the other users, if we check Donnie with elbow, which is correct, and Donnie with elbow spelled incorrectly because Donnie fat-fingered it, you'll see that we only return a 1 for the case where the username and password absolutely match. All right, so getting back to our next topic here. So that was hashing. Now let's move on to encryption and talk about encryption keys. So what is an encryption key? Well, it's very basic. An encryption key is a number or a set of numbers, and they can vary in size and complexity. And the role of an encryption key is to specify how to convert from plain text, which are the values we can read, to ciphertext, which is the encrypted value that we cannot read. Usually an encryption key will not be the password. So if you have an environment where you type in a password to get at something that is encrypted, ideally that password is not the key itself. And the reason for that is because we as humans are typically really bad at picking passwords. There's a good comic on XKCD a few years ago that I love to use about this. It demonstrates, basically they go through and calculate the difficulty and how hard it is for a computer to guess passwords. And the summary at the bottom there is, through 20 years of effort, we successfully trained everyone to use passwords that are hard for humans to remember, but easy for computers to guess. So rather than using complex characters, you're better off choosing a longer password, perhaps one that's made up of a couple different words or forms some kind of nonsensical sentence, and that would actually be much harder for a computer to guess than trying to do something that seems hard to us and is more difficult to remember but really isn't that difficult of a password. It's always better for a password to protect an encryption key than for a password to be the key. When you have a password that protects a key, that typically implies that key was generated randomly or through some complex process and is much better than anything you and I would think up on our own heads. SQL Server and Windows use a key hierarchy to structure keys and protect other keys with keys. So the idea of the key hierarchy here is that all keys need to be protected by something. You just can't have a key sitting out there in the open. Someone can get a hold of it and do bad things with it. So each key is protected by something, and each key doesn't encrypt a whole lot of data. And the reason for this is because if you ever need to change a key, you now have to go back and re-encrypt all the data that key protects with a new key. So if each key doesn't encrypt a whole lot of data, then there won't be a whole lot to change if that key needs to change. If a key changes, all its data must be re-encrypted. So Microsoft has this wonderful graphic here explaining the key hierarchy, which does a better job than I can ever do, so I copied it and credited them. And starting at the top here, you'll notice that, and we'll discuss what these keys are in just a moment, but the Windows operating system level data protection API protects the SM key. That's the SQL Server Service Master key. And then the data below it in the yellow box there, the DMK, the database master key, is protected by the service master key, which is created by SQL Server Setup. And then from here on, you'll see all these different colored boxes. And basically the way this works is each box is protected by the boxes above it. So if we start with the blue box there that says certificate, certificate can be protected either by a password, the PW box, or by the database master key. Next to certificate, an asymmetric key can be protected by a database master key, a password, or the extensible key management module, which is outside of the scope of this session. The big orangey box below that, the symmetric key. A symmetric key can be protected by a certificate or an asymmetric key or the EKM module or another symmetric key or a password. And then encrypted data can be protected by either a symmetric key or a password. So it's kind of neat how this is all structured, and I think this graphic does a wonderful job with it. So to talk about symmetric keys now, symmetric keys are stored in the database they're created in, and they can encrypt data or other symmetric keys. They can be encrypted by other symmetric keys, as I just said, but not the database master key. That's a special case. You cannot encrypt a symmetric key with a database master key. And they can also be encrypted by other asymmetric keys or certificates or passwords or any combination of the above. You can actually protect a symmetric key with more than one of these things, and that gives you a lot of flexibility. Let's say perhaps you have multiple users who each need a password to access this key. If every user's password is different and one of those users leaves the organization, all you have to do is remove their password from protecting that key, and everyone else can go on unaffected. It's not like you have to tell everyone else, hey, there's a new password now that you need to memorize instead of the old one. Because symmetric keys live in the database, they're backed up and restored with regular database backup, which is wonderful. These keys actually cannot be backed up or restored individually. Some of the other ones can, but symmetric keys cannot. Basically, if you need to recreate or restore effectively a symmetric key, if you were to create another key with the same password, it's the same. Each symmetric key has a GUID. That GUID is stored with the data that it encrypts, and it allows you to make sure you have the correct key when you are decrypting that data. There is a whole slew of algorithms available for symmetric keys in SQL Server. Lots of choices here. You'll notice the AES 128, 192, and 256 are in bold. Those are the three that are not decrypted in SQL Server 2016. Everything else that is not bold is deprecated in SQL Server 2016. So if you're doing new development in 2016, you really should be using an AES algorithm. The DES algorithms are older. They've been around for a long time and they're widely supported, but they do not offer nearly as much security as the newer algorithms do. I said AES are where you want to go. 192 is generally sufficient. 256 is stronger, better. Will take a little longer, a little more CPU oomph to decrypt. RC algorithms, Microsoft does not recommend using these anymore. And then if you want to use any of those non-AES algorithms in SQL Server 2016, you need to have it set in compatibility level 120 or lower. Otherwise, those will not be available. Now we have the service master key, which we talked about briefly. It was at the very, very top of our hierarchy graphic from before. This is actually generated when you start up SQL Server for the first time. So as soon as you install it and start it, the service master key is generated. It's a symmetric key. It's an AES 256 key. Prior to SQL 2012, it was actually a triple DES algorithm on that key, but then in 2012 they changed it to AES 256. This key is stored in the master database, and there is no user retrievable password that protects it. It is only used to encrypt database master keys, and that is optionally, as we'll see, linked server passwords, and then credentials. This key, as I said, is not protected by a password. It is encrypted by both the Windows Data Protection API and the service account, and the Data Protection API and the local machine key. So there's actually two different ways this key is encrypted, and every time SQL Server starts, it's going to go ahead and check both of these methods and make sure it can still get at that key. If one of them doesn't work, it will use the other method to go back and correct. You can change or regenerate this key. That will require re-encrypting everything this key protects, but as we just saw on the previous slide, there isn't a whole lot of things this key really protects, so it shouldn't take very long. And because it lives in the master database, whenever you back up or restore the master database, this key will be backed up or restored along with it. You can also back up this key individually. If you don't want to back up the entire master database to get a copy of this key, you can use the T-SQL syntax backup service master key, and it will back up that key to the file of your choosing. All right, so the database master key. These live at the level of the database instead of at the level of the server, and these are not generated by default. So when you create a new database, you do not automatically get a database master key. You have to actually explicitly specify you want a database master key to be created, and you do that using the create master key syntax. This is also a symmetric key, uses the AES 256 algorithm again, just like the service master key. And a database master key must be protected by at least one password. You can have more than one, but you need to have at least one. And it is stored in the database where it's generated, which makes sense because it lives at the database level. So the database master key has opt-out protection by the service master key. So by default, when you create the database master key, it will be protected by the service master key, but you can opt out of that protection and have it protected only by a password instead. But by default, it will be protected by the service master key as well. All right, the database master key is used to encrypt certificates that live in that database, any asymmetric keys that live in that database, and it cannot encrypt symmetric keys. Because it lives in the database, it can be backed up and restored with that database. It can also be backed up separately, which will require a password. You need to specify a password to protect the key in the backup file. But the syntax is backup master key, and you have to use syntax to open the key before you back it up. So that's symmetric keys. To move on to asymmetric keys, they're a little different because that key lives in two parts now. There's a public half of the key and the private half of the key. As I said, the private key is secret. You keep that to yourself and never share it with anyone at all. And the public key is something you would share with others, or in fact, broadcast. It's not uncommon to see people putting a public key on their website or whatever for verification purposes. So the way asymmetric keys work is if we're going to send a message, so in this example from Microsoft again, let's say that Krishna in the first row there is sending a message to Alice. Krishna has her plain text, and she is going to encrypt her plain text with Alice's public key. She can get Alice's public key because it's public and Alex has shared it with the public. And by encrypting this message, it produces ciphertext, which is the little yellow box there. That ciphertext now can only be decrypted by Alice's private key. So Alice gets a hold of the message, uses her private key to decrypt the message, and she can now read the plain text. This is the basic of asymmetric key encryption and decryption. Anything encrypted with the public key can only be decrypted with the private key, and anything encrypted with the private key can only be decrypted by the public key. In SQL Server, we would use asymmetric keys to encrypt symmetric keys. Remember that problem I talked about earlier where we have the issue of needing to get our symmetric key to someone else? Well, if we use asymmetric encryption to encrypt that symmetric key, we can now make sure that only our intended recipient can get that key. We just transferred it securely, and now they can use the symmetric key to decrypt our secret data. You can also use asymmetric keys to sign data. If you had a document and you wanted to make sure that document was not changed, a common method of signing would be to actually create a hash of that document and then encrypt that hash with your private key. Anyone could then decrypt that hash with your public key and then compare the hash to the document and tell that the document is in fact authentic. You can also use asymmetric keys to secure data itself. However, this is not really recommended. Asymmetric encryption is much slower than symmetric encryption. And in SQL Server, the size that you can encrypt via asymmetric keys is limited, and it's something rather small. I remember it being along the lines of like 117 bytes. So your options are limited with that. Asymmetric keys can be secured by the database master key or by the password, one or more passwords, or by the EKM module, if you have that in your environment. So with asymmetric algorithms, there's really only one family of algorithm in play in SQL Server. That's the RSA family. There's a bunch of different lengths available. You'll notice that only 3 of them are in bold. So the 512 and 1024 lengths are deprecated in 2016. They're still available, but your database needs to be in compatibility level 120 or lower. However, it is recommended you use 2048, 3072, or 4096 bits. As I mentioned, these are significantly slower compared to symmetric key algorithms. So we have our asymmetric key pair. We have our public and our private key. Keeping them together for transport, or only part of them for transport, can be an issue. And that's typically where certificates like to come into play. So SQL Server does have the concept of certificates. And certificates are essentially a package for storing and transporting asymmetric keys. Certificates are stored in databases, and you can use them to encrypt asymmetric keys or sign data, as I explained with asymmetric keys earlier, or to encrypt connections for things like SQL Server Service Broker or database mirroring, where we'd all use certificates. The way I like to think of certificates are if a asymmetric key pair is a pizza, a certificate would be along the lines of a pizza that has been packaged for delivery. So we get the pizza, we still get the certificates, or the keys, we get the pizza, but we get a little bit more too, right? We got pizza, but now the pizza's in a box. We have some extra things alongside with it. We have the yummy garlic dipping sauce that so many people like, and then we have that pepper over there that nobody I know ever bothers to eat. So a certificate is really taking these asymmetric keys and packaging them with extra things, with metadata in this case.
Hey, Bob.
So, yes, sir?
Can I pass along a quick question?
Sure.
Vanessa asked if you can explain the purpose of key signing parties a bit. She's assuming that's only helpful if you know who you'll be communicating with, and collecting other people's keys who you won't be. Trading data with is useless, right?
Well, e-signing can be used to, if you know who you're sharing your data with, but it also could not be, right? I could post a document publicly on my website and post a signature for that document, maybe as I mentioned, a hash of the document that I've signed with my private key. Then anyone looking at my document on my website could take my signature, decrypt the signature with my public key, which would also be posted, publicly either on my website or wherever, and then use it to authenticate what they're reading. So you could use multiple asymmetric keys to control who can see your document. I don't have a graphic of this, but if I was sending a document to someone else, I could encrypt it with the recipient's public key and then with my private key. And when the recipient gets it, they'll have to use my public key to decrypt it, so they'll know it came from me. And because I encrypted it with the recipient's public key, they'd have to use their private key. So now we get two things. Now, not only is the document encrypted twice, they can be sure it came from me, and they can be sure that they're the only ones that were able to see it. So you can kind of layer them in that way. But as far as signing goes, you could sign with the intent of controlling your audience or not, is how I've always seen that. Hopefully that answers the question.
Yeah, Vanessa says, yeah, I think so.
Okay.
Thanks.
Okay. All right.
And
No problem.
another question just popped up. Yahalem asks, all these are for data at rest, not data in transit or data in memory, right?
That is correct. Everything we're talking about at the moment is about data and rest. We'll have a little talk on other SQL Server capabilities towards the end that cover more of the data in transit scenarios.
All right, thanks. That's all the questions right now.
All right, excellent. So moving on from our picture of the lovely pizzas here. SQL Server uses standard X509 certificates, and as I said, a certificate is more or less a container that contains the asymmetric key, the pizza, and some extra things, some metadata to go along with it. Certificates can be created by you or issued by a certification authority. Depending on what your needs are, you may need one that's issued by an authority, but for experimental use and for within an office, a lot of times certificates will just be issued by a local authority, which is either yourself or a system administrator or something along those lines. SQL Server doesn't always check all the fields in a certificate. There's the certificate authority field and the subject field that it doesn't always check. There's also an expiration date in a certificate that SQL Server's data encryption functions ignore. So we're going to talk shortly about transparent data encryption in SQL Server. TDE ignores the expiration date on the certificate. And that's a good thing, because if your certificate expired and TDE cared, then you wouldn't be able to read the data anymore, and that'd be bad. However, Service Broker in SQL Server does check the expiration date. So if you're using certificates for Service Broker, you'll want to be mindful of when your certificates expire, because once they expire, Service Broker will no longer recognize them and your process will break. To back up a certificate, they're backed up with the database. You can also back up certificates to an individual file. And if you want to back them up to a file and you want the private key half as well, you have to write the private key out to a separate file in the backup syntax for certificates. And when you restore a certificate from a file that you backed it up to, that's easy. You can create a certificate from a file, which is essentially restore, and that may or may not contain the private key, depending on whether or not you have the private key and whether you choose to restore the private half as well. That's certificates in a nutshell. So we mentioned just briefly before transparent data encryption. So SQL Server introduced transparent data encryption in SQL Server 2008. Transparent data encryption, it's important to remember, it encrypts data when it's on disk, and only when it's on disk. Nowhere else is it encrypted. So in our very simplified example of a system here, we have our end user. User is querying data, which involves contacting access methods, and then reading data from memory, and then perhaps reading data from disk as well. In our very simplified database hierarchy here, when we go ahead and we deploy transparent data encryption, the only thing that's encrypted is literally what's on disk. As soon as that data is read out of disk and put in memory, stuck in the buffer pool, it is no longer encrypted. It is only encrypted when it sits on the disk. Because of this, the encryption is transparent to your applications, right? Your applications have no clue whether or not that data is encrypted. They don't care. They don't need to. The only place it's encrypted is when SQL Server is reading it from disk. This is great. That's why it's called transparent, because you don't have to change anything in your application. Literally, you can continue talking to an encrypted, with a TDE encrypted database, just like any other database. The protection this offers you is from theft of disks, and really, that's about it. If someone were to walk into your data center, which hopefully they can't because it should be physically secured, and if you don't have physical security, you really don't have anything. But if they were to somehow get in your data center and rip disks out of your database server, you would be protected if you had transparent data encryption. Aside from that, you don't get a whole lot of protection. You get encryption of your backups. You get that with transparent data encryption simply because the backup process reads the data from the disk and now that the data on disk is encrypted, the backup will be as well. TempDB is also encrypted when you deploy transparent data encryption. TempDB often contains data from the database that's encrypted, or can, and because of that possibility of TempDB containing encrypted data, TempDB goes ahead and becomes encrypted too as soon as any database on your instance has TDE enabled. Aside from that, transparent data encryption does nothing to protect you from unauthorized queries. If someone has, gains credentials that they shouldn't have, or otherwise infiltrates your network and gets access to a SQL server, transparent data encryption will protect you from nothing. It's transparent. They can query an encrypted database just as effectively as an unencrypted database. Transparent data encryption also does not encrypt file stream data. If you're using file stream capabilities in SQL Server, that is stored separately. That is not part of encryption either. The way transparent data encryption works is it uses a certificate in the master database to encrypt a key. And then that key is used to encrypt the database. If you take a backup of a TDE encrypted database and go to restore it elsewhere on another machine, you need that key or that certificate. If you don't have the certificate, then you can't restore the database, period. So if you're using TDE, you want to make sure you have those certificates backed up somewhere that you can get to them if there's an emergency or whatnot. Otherwise, your database backups are completely useless. When you enable transparent data encryption or disable it, the encryption and decryption operations actually take place in the background, which is wonderful. You can just sit there and they will happen transparently while user queries are going on. And they are Enterprise Edition only for transparent data encryption. And if anyone's aware, Microsoft made some significant announcements just yesterday about a bunch of Enterprise Edition features in SQL Server 2016, which are being removed from Enterprise Edition and opened up to SQL Server 2016 Service Pack 1 Standard Edition as well. Transparent data encryption was not included in this list of features. They opened up a bunch of stuff, but TDE wasn't one of them. So if you have SQL Server 2016 Service Pack 1, you'll get a whole bunch of new goodies in Standard Edition, but transparent data encryption is not one of them. Moving on to backup encryption. So we've spent all this time talking about protecting our databases and our data, but what about our backups, right? If someone can get a hold of a backup and restore that backup elsewhere, now they have all the data, and chances are you might not even know about it if you're not monitoring where your backups are stored. So whenever we're talking about backups in general, make sure you know who can access them, who has access to the shares or the tapes or wherever they may be stored in your organization, because being able to query a database is extremely powerful, but being able to take a backup and restore it elsewhere and query it or crack it or do whatever you want with it on your own time is even more dangerous. Yeah, loss of backups can be a bigger threat than the database itself. So in SQL Server 2014, they added the backup encryption feature as a native option with backups. Previously, if you wanted to encrypt just a backup and did not want to enable transparent data encryption, you had to utilize third-party tools. But now, as of SQL Server 2014, this is a natively available feature. And it works in Standard Edition, and it always has worked in Standard Edition, so that was very nice as well. Much like transparent database encryption, backup encryption utilizes encryption provided via a certificate or an asymmetric key that live in the master database. Older versions of SQL Server cannot read encrypted backups. The ability to read an encrypted backup is only present in SQL 2014 and newer. And if you have an existing backup, you cannot apply backup encryption to it. You would need to retake that backup. And the syntax to create an encrypted backup is actually wonderfully simple. It builds on the backup syntax we already know and love. You simply add a with encryption statement, and then you get to specify what type of algorithm you'd like to use and the certificate that you would like to use to make that backup. And once again, just like transparent database encryption, you need to make sure you have a copy of this certificate stored safely somewhere else off the server. So if you end up having to restore that server for whatever reason, including an emergency, you have that certificate present to be able to read that backup. Finally, beyond backup encryption, the last capability we're going to touch on extremely briefly is SQL Server 2016 Always Encrypted. And this is a topic that is worthy of its own presentation and has gotten them in the past. So we're just going to touch extremely briefly one slide on Always Encrypted. It is a new feature in SQL Server 2016. Essentially, the way it works is that the data is encrypted at the client and transferred to the SQL Server in an encrypted state and stored in SQL Server in an encrypted state. The idea is the data is protected from the database administrators as well. No one should be able to see it except the client application. And you'll notice I put multiple asterisks after that because it's a little more complicated than that, but again, that's outside the scope of today's presentation. The database only knows encrypted data, like I said, and the DBA only knows encrypted data as well. So if you have extremely sensitive data, this may be something for you. And then finally, as of yesterday, Always Encrypted is no longer an Enterprise Edition only feature. As long as you're running SQL Server 2016 Service Pack 1, it will work in both the Standard and Express editions as well. So that is the conclusion of my presentation today. If anyone has any extra questions, I'm happy to answer them, or you can also reach out to me via email or Twitter, or check out my blog, and I'll be happy to address any other questions there as well.
Hey, Bob, we just had another question come in.
Okay.
Nahalium asks, how about backup encryption with password? Is that deprecated?
Backup encryption with password. Yeah, backup encryption with password, it is most definitely deprecated, and I almost want to say it's been removed from 2016. I'm not totally sure about that.
Yeah,
backup
I believe it was removed.
Okay. Backup with password was never encryption at all. It was the backup itself was unencrypted, and literally all it was SQL Server would verify the password before performing the restore. But if you could find a way to crack that password via brute force or somehow remove that information from the backup file if you knew the format, the backup itself was not encrypted at all. So I believe Microsoft got rid of that feature simply because it was providing a very, very false sense of security.
Ella asks, can you encrypt existing data with Always Encrypted?
Can you encrypt existing data with Always Encrypted? I am not sure. I do not have a whole lot of information on Always Encrypted. I have not deployed it in any of my environments. Based on what I know and the fact that the entire premise is that the data is encrypted at the client, I believe this is something you need to design your application to accommodate from the beginning. It's not something you would simply turn on and enable encryption for like you could for something like transparent database encryption. So I'm going to say no.
Yeah, my understanding, and though likewise I haven't done it myself, but my understanding is if you want to encrypt existing data, the recommendation is to create a new table and move the data into it, encrypting it as you move it, and then start using the new table.
Okay, it sounds that makes sense based on my understanding as well.
And MK asks, can you explain the data in transit encryption options, such as self?
Okay. Yeah, I didn't really touch on those in this presentation. There are data in transit encryption options in SQL Server. You can enable SSL on connections, and you can choose whether or not SQL Server requires or simply recommends, if available, those levels of encryption as well. This will encrypt the channel between users querying the database and the database. So essentially, in that case, you would get protection from people maybe sniffing your network and watching the data come across in plain text. This way, it would be an encrypted conversation between your application and the database. Yeah, I didn't really touch on that in this session, and I'm sorry for that. But essentially, those are your options with that.
Okay. And Alina asks, what is the best way to encrypt or protect data in Azure SQL DB?
Oh boy, okay, yeah, that is definitely outside the scope, and I do not work with Azure. My environment is totally on-prem, so I do not feel safe answering that question simply on lack of knowledge on my part.
Likewise, I have nothing to add as far as Azure. I don't know what the story is there exactly for
Yeah.
encryption. Um, I don't know if you would have time for this, but Kieran asked if you can provide step-by-step database encryption for a database. Just do a quick demo of encrypting a database.
I do not have a demo environment where I can do that at the moment. Not to mention it would involve a lot of typing. And if they were to reach out to me, perhaps I could point them in the direction of a blog post that would already do that. I'm sure Microsoft already has that well documented as well.
Lots of people thanking you and saying great presentation.
Well, thank you very much, everyone, for coming today and giving me an hour out of your day to listen to this. I appreciate it very much. And like I said, if you have any further questions, feel free to contact me directly with my email on the screen.
Great. Thank you very much, Bob. And thank you, everybody, for attending.